Okay, in this video I'm going to talk about the concept of angular momentum. So basically that's momentum that has to do with rotation, okay? And we're going to use the analogy with the linear momentum. So with linear momentum, we had momentum equals m times v as a vector, right? Now, the analogy is just going to be angular momentum, which is really a vector quantity, but we're going to look at it for the most part as a scalar quantity. Now, don't ask me why they call it L, I don't know. The mass is replaced with rotational mass, and then omega as a vector quantity. Again, we're not going to be looking at the vector aspect of this quantity here. Most likely, we're going to be looking at the scalar aspect. But when we do, we're going to have to try to explain some phenomenon that happens with the vector quantity. So when we do some demonstrations in class, we have to bring in the vector nature of this L. Now, we learned also that in order for your momentum to change, you have to have an impulse. So I'm going to write this as imp. Okay, not to confuse it with I. An impulse is F times t. So in order for your momentum to change, this is all vectors here, okay? In order for your momentum to change, you have to apply a force for a period of time, okay? And that should, now, if there is no external impulse on the object, then your momentum is conserved. So we're going to say that your initial momentum equals your final momentum as vectors if impulse equals 0. So basically, if there is no force, if there is no net force, if the net force is 0. Okay, well, same thing here. In order for your angular momentum to change, and I'll do this as scalar, you have to have some kind of like rotational impulse. Now, F is replaced with torque, and this is the net here in both cases. So you have to have a torque that's applied for a period of time, which kind of makes sense, right? If you want something to go faster, you have to apply a torque, to rotate faster, in other words, right? In here, the initial angular momentum is equal to the final angular momentum if there is no net torque, okay? Now let's talk a little bit about the vector nature of L. The rules, it's going to be the right-hand rule is the same rules as for omega. In other words, the vector, the angular momentum vector, is going to be pointing in the same direction as the angular or rotational speed, angular speed, okay? So that's that. So this is extremely important, this part here. Momentum is only conserved if there is no external torque. Now, if I have an object spinning in this direction, okay, you can see clearly that omega is going into the board. Well, L also is going into the board. So we're going to use this for some demonstrations tomorrow, trying to explain something with the bicycle wheel. Okay. So I'm going to write this up top. Li equals Lf if the net torque is 0. Okay. And I think we also say that delta L is equal to the net torque times the time during which this torque is applied. Now, if I want to find L for a single particle going around an axis of rotation, okay? Now, L is I times omega, which is equal to, now for a single particle, the I is mr squared, r being how far is this object from the axis of rotation, times omega, which is v over r. So for a single particle, it should be just mv r. That's also true for a hoop, okay? We're going to be using that a lot. Now, how do we explain how ice skaters go fast okay, or faster as they bring their arms in compared to when they have their arms out? Well, explanation is very simple. So Li equals Lf, which means the I initial, the omega initial, I could have written this as zeros, equals the I final times the omega final. So in other words, that product has to stay constant as long as there is no external torque. And there is no external torque. Okay. If they start in a position with their arms out, this I is greater than the final, because when they bring their arms in, the mass is closer to the axis of rotation, which is going through them vertically. Okay, so this IF goes down. Okay, in order to keep this product constant, this WF, this omega F, has to go up. That's what makes them go faster, because their moment of inertia now is less. Okay, so this is less, that's going to go up. So if they want to slow down, they bring their arms out, their I goes up, which means their omega will come down. And we'll do some stuff like this in class tomorrow. So let's do an example here. Let's say I have a very light rod, and the axis of rotation is here. So let's just say this T kind of turns this way, comes at you, and it goes into the board. Okay, and I have a mass sitting right here, mass M, and I have another mass M here, and this length here is L, and this is L. Okay, now I want to compare the angular speed of this to another one where it's the same length of the rod, but this time I'm not going to put the masses at the end, I'm going to put them halfway. In other words, this is L over 2 and L over 2, and it's the same mass. So let's see what we can do here. Well, the I here is going to be mL squared. That's how far this is from the axis of rotation. But you have two of them, so it's 2 times. Okay. The I here is going to be mL over 2 squared, but you have 2 of them. Okay, and that should be equal to mL squared over 2 by the time you finish, right? Now you can see clearly that the I here, so if I call this the initial and this the final, this is going to be 1/4 of this if you were to compare them, right? Okay, so this is going to be 1/4 of the initial I. So it kind of like follows a square proportion property, right? Okay, so in other words, when you come closer, your I will drop by the ratio of these two distances here. So if I came 1/3 of the way, this will be 1/9. So which means if I was going at speed of omega O here, my final speed here will just be 4 times as much. Okay? Now that's conceptually. I think you can do the math here, and let's see what the math gives us. So if I do IO, omega O, there's no external torque, equals IF times omega F. Well, this is 2m L squared times omega initial equals m L squared over 2 omega final. And you will find that omega final is 4 times as much. Okay. The other thing is when we do Li equals Lf, or I initial, I'm going to write this as O. I initial, omega initial equals I final, omega final. Now these omegas, they don't have to be in radians per second in this case. As long as they are in the same units, RPMs or RPS, you're okay. So if this omega initial is in RPM, this omega final will be in RPM. Okay? Your masses, they can be in grams. Okay? It's okay. Your distances can also be in centimeters or meters or yards. It doesn't matter. Okay? And I think that should do it for for this video.
All right, I'm out. Peace.